Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should truly twist your perception of reality. Right now, as you listen, a galaxy more massive than our own Milky Way, containing perhaps 1 trillion stars, is hurtling towards us at 110 kilometers per second. That's about 68 miles per second. This isn't some distant, abstract cosmic event. This is our very nearest galactic neighbour, the Andromeda Galaxy, and it's on a collision course with us. Yet despite this seemingly terrifying speed, we won't actually collide for another 4.5 billion years. Think about that for a moment. 10 kilometres every single second for 4.5 billion years, and that's how long it takes for two of the universe's most colossal structures to meet. This paradox of immense speed over unimaginable timescales, leading to a future event that is both inevitable and incredibly distant, highlights the mind-bending scales we deal with when we talk about galaxies. The very idea of two galaxies colliding conjures images of chaotic destruction, stars smashing into each other, planets obliterated. But the universe at these scales is mostly empty space. So much empty space, in fact, that when Andromeda and the Milky Way eventually merge, the stars within them are statistically unlikely to even touch. It will be more like two clouds of dandelion seeds passing through each other, with only the occasional rare interaction. Yet the galaxies themselves will merge, their gravitational pulls intertwining, reshaping and eventually forming a new, larger galaxy we've affectionately dubbed Milkomeda. This isn't just a theoretical prediction, it's a cosmic dance in slow motion, observable through the subtle shifts in Andromeda's light, a testament to the colossal forces at play across the vast emptiness of space. And it all begins with understanding just how truly immense Andromeda is. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a mind-bending question. How can something be so incredibly close, astronomically speaking, that it's on a direct collision course with us, yet also so unimaginably far away that its light has travelled for millions of years to reach our eyes? This is the paradox of the Andromeda Galaxy. It is our closest galactic neighbour, the largest member of our local group of galaxies, and it's the only major galaxy that isn't moving away from us due to the expansion of the universe. Instead, it's coming straight for us. But when we look up at the night sky and try to spot it, it's just a faint, fuzzy patch of light, barely visible without dark skies and keen eyesight. This seeming contradiction is the key to truly grasping the scale of Andromeda, and, by extension, the universe itself. To understand how big Andromeda really is, we first need to appreciate the distances involved. What exactly is a galaxy? Imagine a vast cosmic island, not of land but of stars, gas, dust, and an invisible mysterious substance called dark matter, all bound together by gravity. Our own galaxy, the Milky Way, is one such island, a majestic spiral with the central bulge, a thin disk, and sweeping arms. It contains somewhere between 100 billion and 400 billion stars. Now, picture another such island, Andromeda, which is even larger, potentially containing up to 1 trillion stars. That's a 1 followed by 12 zeros. It's also a spiral galaxy, quite similar in structure to our own, but more massive, more luminous, and perhaps a bit more majestic. The distance separating us from Andromeda is not something we can easily conceptualize with everyday units like miles or kilometers. If you were to express it in miles, you'd be looking at a number like 1.5, 10 to 18 miles, or 15 followed by 18 zeros. That number is so large it becomes meaningless. This is why astronomers use a different unit, the light year. A light year is not a measure of time, but a measure of distance. Specifically, the distance that light travels in one Earth year. To appreciate this, we need to consider the speed of light. Light in a vacuum travels at an astonishing 2,758 meters per second, which is approximately 186,282 miles per second. To put that in perspective, a beam of light could circle the Earth about 7.5 times in a single second. It takes light about 1.3 seconds to travel from the Moon to Earth, and about 8 minutes and 20 seconds to travel from the Sun to Earth. These are distances within our own solar system which already feel vast. Now, extend that to a full year. In 1 year, light travels roughly 9.46 trillion kilometers, or about 5.8 trillion miles. This is 1 light year. Andromeda, our closest major galactic neighbour, is approximately 2.5 million light years away. This means that the light we see from Andromeda tonight left that galaxy 2.5 million years ago. When you look at Andromeda, you are literally looking back in time. You're seeing the galaxy as it was when early hominids were just beginning to walk the Earth. Any star that might have exploded in Andromeda 100,000 years ago, or a new star that might have formed 1 million years ago, we won't know about it for millions of years to come because the light carrying that information hasn't reached us yet. This concept of looking into the past is one of the most profound implications of cosmic distances. Despite being 2.5 million light years away, Andromeda is still one of the few galaxies visible to the naked eye from Earth, appearing as a faint, elongated smudge in a dark sky. Its apparent size in the sky is quite remarkable, actually. If you could see its full extent clearly, it would appear about 6 times wider than the full moon. Imagine 6 full moons lined up side by side in the sky. That's the angular size of Andromeda. Yet, because its light is so spread out across that vast area, our eyes can only pick out the brightest central region. This combination of vast distance and significant angular size hints at its truly colossal physical dimensions. But how do astronomers measure such immense distances with any precision? It's not like they can stretch a tape measure across the void. One of the most crucial tools in this cosmic toolkit is the use of standard candles, objects with a known intrinsic brightness. For distances within our local group like to Andromeda, the most famous and reliable standard candles are a type of star called Cepheid variables. These are pulsating stars that regularly brighten and dim in a predictable cycle. Crucially, in the early 20th century, astronomer Henrietta Swan-Leavitt discovered a direct relationship between a Cepheid's pulsation period and its absolute luminosity, how truly bright it is, regardless of its distance from us. If you know how fast a Cepheid pulsates, you can determine its intrinsic brightness. Then, by comparing that intrinsic brightness to how bright it appears from Earth, you can calculate its distance. It's like knowing the wattage of a light bulb and then judging its distance by how dim it appears. Edwin Hubble in the 1920s famously used Cepheid in Andromeda to definitively prove that it was not a nebula within our own galaxy, but an entirely separate island universe far beyond the Milky Way. This discovery fundamentally changed our understanding of the universe, expanding it from a single galaxy to a vast cosmos of billions of galaxies. So we've begun to grasp the incredible distance to Andromeda, a distance so vast that it forces us to confront the past and rethink our everyday units of measurement. We understand that this distance, measured in light years, is the key to appreciating its true scale. In the next chapter, we'll take this understanding of cosmic distance and apply it directly to Andromeda's physical dimensions, truly exploring just how enormous this approaching giant really is, and what it means for the stars and planets within it. We left off marvelling at Edwin Hubble, the visionary who, with the help of those incredible standard candles, proved Andromeda was not just a nebula within our own galaxy, but an entirely separate island universe. But how did he do it? How did one man, with a telescope and a keen eye, measure something so unfathomably distant that it completely rewrote our cosmic address? The secret, my friends, lies in the stars themselves, specifically a very special type of star called a Cepheid variable. Imagine, if you will, a street lined with light bulbs. If you know how bright each bulb truly is at its source, its intrinsic luminosity, then simply by observing how bright it appears to be from your vantage point, its apparent brightness, you can calculate its distance. A dim-looking bulb that you know is intrinsically very bright must be far away, right? Conversely, a dim-looking bulb that you know is intrinsically faint must be quite close. This brilliant concept became a cosmic yardstick, but it wasn't Hubble who first calibrated it. For that, we turn our gaze to a true unsung hero of astronomy, Henrietta Swan Leavitt. Back in the early 20th century, Leavitt was one of a group of women known as computers at the Harvard College Observatory. Her job was to meticulously analyze photographic plates of stars, cataloguing their brightness. She spent years studying variable stars in the Magellanic Clouds, two small galaxies orbiting our Milky Way. What she discovered was nothing short of revolutionary. Leavitt observed that a particular class of pulsating stars, the Cepheid variables, had a direct, predictable relationship between their pulsation period, how long it took them to brighten and dim, and their intrinsic luminosity. The longer a Cepheid took to pulsate, the brighter it intrinsically was. Think of it like a cosmic heartbeat. A slow, powerful beat meant a vastly luminous star, while a quicker pulse indicated a less brilliant one. This was the period luminosity relationship, and it provided astronomers with the first reliable standard candle that could be used to measure truly immense cosmic distances. Armed with Leavitt's groundbreaking discovery, Edwin Hubble turned his mighty 100-inch Hooker telescope at Mount Wilson towards that faint, fuzzy patch in the constellation Andromeda. Night after night, in the early 1920s, he painstakingly photographed Andromeda, searching for those telltale blinking beacons. And there they were, tucked away in the spiral arms of what we now know as Andromeda. Hubble found Cepheid variable stars. He measured their pulsation periods. He noted their apparent brightness. Then, with Leavitt's period luminosity relationship as his guide, he calculated their intrinsic brightness. The difference between their true brilliance and how dim they appear to be was staggering. The numbers didn't lie. These Cepheids, and therefore the entire Andromeda Nebula, were not just outside our solar system or even our galaxy, but millions of light years away. This was a paradigm shift of epic proportions. It wasn't just our galaxy. The universe was teeming with countless other galaxies, each a sprawling metropolis of stars, gas and dust. Andromeda was confirmed as an island universe unto itself, vastly expanding humanity's understanding of the cosmos. The universe, we suddenly realized, was far grander than anyone had ever imagined. Now that we understand how we measure such distances, let's talk about the sheer mind-bending scale of Andromeda itself. We often throw around terms like millions of light years, but what does that even mean? A light year, for those of you who might need a refresher, isn't a measure of time but of distance. It's the incredible distance that light, the fastest thing in the universe, travels in one Earth year, approximately 9.46 trillion kilometres, or about 5.88 trillion miles. So that when we say Andromeda is 2.5 million light-years away, we're talking about a distance so vast it almost ceases to be comprehensible. Andromeda, however, isn't just distant, it's colossal. When we finally managed to accurately measure its physical dimensions, the numbers were truly awe-inspiring. Our Milky Way galaxy, while respectable, spans about 100,000 light-years across. Andromeda, our approaching giant, stretches a staggering 20,000 light-years. From one side to the other, imagine that. Light, travelling at 300,000 kilometres, 86,000 miles per second, would take to 20,000 years just to cross it. It's more than twice the width of our own galaxy. And within that immense expanse, how many stars do you think reside? While our Milky Way is home to an estimated 200 to 400 billion stars, Andromeda is a true stellar leviathan, boasting an estimated 1 trillion stars. Yes, you heard that right, 1 trillion. That's more stars than grains of sand on all the beaches of Earth, packed into a single breathtaking cosmic structure. Each one of those stars could potentially host its own planetary system, its own stories, its own possibilities. The sheer scale is almost too much for our minds to grasp, isn't it? Andromeda's mass is equally impressive. It weighs in at an estimated 1.5 trillion times the mass of our Sun. This immense gravitational pull is precisely why it's hurtling towards us. But here's a fascinating twist. Only a fraction of that colossal mass comes from the visible stars and gas we can observe. The vast majority of Andromeda's gravitational heft, like that of all large galaxies, comes from the mysterious invisible substance we call dark matter. This enigmatic material, which we still can't directly detect, forms a vast, diffuse halo around the galaxy, extending far beyond its visible light, providing the gravitational scaffolding that holds this cosmic titan together and dictates its movements through space. It's truly an invisible giant, in more ways than one. But what does Andromeda actually look like up close, if we could somehow zoom there instantly? It's a majestic spiral galaxy, much like our own, but grander. From a conceptual vantage point, we would see sweeping, majestic spiral arms, teeming with young, hot blue stars, glowing nebulae, and dark lanes of cosmic dust where new stars are being born. These arms wind outwards from a brilliant yellowish central bulge, a dense ancient heart where older, redder stars reside, packed tightly together around what we believe to be a supermassive black hole, millions of times the mass of our Sun. Intriguingly, astronomers have discovered that Andromeda's central bulge isn't just a single unified core. It actually hosts two distinct nuclei, or concentrations of stars orbiting each other. This peculiar feature is a strong indicator that Andromeda itself might have undergone a past galactic merger, perhaps swallowing a smaller galaxy long ago. It's a cosmic cannibal, perhaps, long before its date with us. Andromeda is not just stars and gas. It's also surrounded by a vast, diffuse halo of ancient globular clusters, spherical collections of hundreds of thousands of old stars, and, of course, that invisible dark matter. This halo extends far beyond the bright spiral arms, marking the true gravitational reach of this immense galaxy. So when you next gaze up at the night sky and perhaps catch the faintest glimpse of that ghostly smudge in Andromeda, remember what you're truly seeing. You're not just looking at a faint patch of light, you're peering 2.5 million years into the past, witnessing a colossal spiral galaxy over twice the size of our own, containing 1 trillion stars and weighing 1.5 trillion solar masses. You're seeing an invisible giant, held together by dark matter, hurtling towards us at 110 kilometers per second. We've peeled back the layers of distance, thanks to the ingenuity of Leavitt and Hubble, to understand the true physical dimensions of this approaching Titan. We know its size, its star count, its mass, and even a bit about its internal structure. But knowing what it is and how big it is only leads to more questions. What happens when two such titans finally meet? What will the collision look like? And what will become of our familiar night sky, so irrevocably changed? The journey into Milkomda has only just begun. Edwin Hubble, armed with Henrietta Swan Leavitt's groundbreaking insight, didn't just guess at Andromeda's distance. He performed one of the most pivotal measurements in cosmic history, definitively placing our galactic neighbour 2.5 million light-years away. But how, you might wonder, do we really nail down such an incomprehensibly vast distance? How do we point a telescope at a fuzzy patch of light and say, with such confidence, that light travelled for 2.5 million years to reach us? It all comes back to those remarkable Cepheid variable stars, our cosmic lighthouses. Imagine a lighthouse's beam sweeping across the dark ocean. If you know how intrinsically bright that lighthouse actually is, its absolute luminosity, then by observing how bright it appears to be from your ship, its apparent brightness, you can calculate exactly how far away you are. It's a beautifully simple concept, isn't it? But applying it to the universe required a genius like Leavitt to unlock the secret of the Cepheids. She discovered that these pulsating stars don't just blink randomly. Their period of pulsation, the time it takes for them to go from bright to dim and back again, is directly related to their absolute luminosity. The longer the period, the brighter the star. So astronomers like Hubble could find a Cepheid in Andromeda, measure its pulsation period, then use Leavitt's relationship to determine its true, intrinsic brightness. Once they knew how bright it really was, comparing that to how bright it appeared to be through their telescopes allowed them to calculate the distance with astonishing accuracy. It was like having a cosmic tape measure stretched across the void, with each Cepheid star acting as a precisely calibrated marker. This method, known as the standard candle technique, is still a cornerstone of modern astronomy, allowing us to map the universe on scales that would have been unimaginable just a century ago. So when we say Andromeda is 2.5 million light-years away, we're not just throwing out a number, we're talking about a distance meticulously measured, piece by painstaking piece, building upon the insights of brilliant minds. And what a distance it is! It means that the light we see tonight, shimmering faintly in our night sky, left Andromeda when early humans were just beginning to walk upright on Earth. It's a snapshot of a galaxy as it was eons ago, a profound connection to the deep past. Now that we've established its incredible distance, let's truly appreciate the majesty of Andromeda itself, beyond just its overall mass and width. We've mentioned its colossal size, 220,000 light-years across, containing 1 trillion stars. But what does that look like up close if such a thing were possible? Andromeda is a grand design spiral galaxy, just like our own Milky Way, but arguably even more spectacular. Imagine those sweeping, elegant arms, not just aesthetic flourishes, but vibrant cosmic nurseries. These spiral arms are regions where gas and dust have been compressed by gravitational forces, triggering the birth of new stars. They are streaks of brilliant blue, studded with hot, young, massive stars that burn fiercely and brightly, illuminating the nebulae of gas and dust from which they were born. Between these arms lie older, yellower stars, and vast, dark lanes of cosmic dust, silhouetted against the brighter stellar backdrop, hinting at untold stellar potential. If we could see Andromeda with our own eyes from a short distance, its arms would coil around a central brilliance like a celestial Catherine wheel, a spectacle of ongoing creation and ancient starlight. At its heart, that dense, brilliant central bulge we spoke of is a teeming metropolis of stars. Here, stars are packed so tightly together that the night sky from a hypothetical planet within this region would be ablaze with countless suns, a perpetual twilight rather than true darkness. And nestled deep within this stellar heart, just like in our own Milky Way, lurks a supermassive black hole. Andromeda's central behemoth, known as P3, is estimated to be even larger than Sagittarius A, our galaxy's central black hole, weighing in at perhaps 100 to 230 million times the mass of our Sun. It's a gravitational anchor, dictating the motions of billions of stars around it, a silent, powerful monarch at the galaxy's core. But Andromeda holds an intriguing secret within its central bulge. Not one, but two distinct nuclei. When astronomers peered closely, they discovered a second, fainter concentration of stars slightly offset from the main, brighter nucleus. This isn't just a quirky feature. It's a cosmic fingerprint, strong evidence of a past galactic merger. It suggests that Andromeda, in its long history, swallowed a smaller galaxy, whose core now orbits within the larger galaxy's centre, slowly being assimilated. This ongoing process of galactic cannibalism is a common theme in the universe, demonstrating that galaxies are not static entities but dynamic, evolving systems, constantly growing and reshaping themselves through gravitational interactions. Andromeda isn't just bigger in terms of stars, it's also far richer in its retinue of globular clusters. Remember those ancient spherical collections of hundreds of thousands of stars tightly bound by gravity that orbit galaxies like cosmic beehives? While our Milky Way boasts around 50 to 180 of these venerable structures, Andromeda is estimated to host a staggering 40 or more. These globular clusters are like living fossils, containing some of the oldest stars in the universe, providing invaluable clues about the early formation and evolution of galaxies. Andromeda's abundance of them further highlights its grander scale, and perhaps a more active history of accretion and growth. Andromeda's immense mass, we've learned, isn't just from its visible stars and gas. Remember that invisible scaffolding, that gravitational glue we talked about? The dark matter halo. Andromeda's dark matter halo is truly colossal, extending far beyond its luminous disk, enveloping the entire galaxy in a vast, unseen sphere. It's this dark matter that provides the overwhelming gravitational force needed to hold together a galaxy of Andromeda's size and rotational speed, preventing it from simply flying apart. Without this mysterious, invisible component, Andromeda, for all its visible glory, simply wouldn't exist as we know it. It's a constant reminder that the universe, in its grandest forms, is dominated by forces and substances that remain largely hidden from our direct perception. So we have this magnificent, colossal galaxy hurtling towards us at 10 kilometers per second. We know how we know its distance, and we have a deeper appreciation for its intricate structure. But what does this impending collision, this cosmic ballet, actually mean for us? We've established that individual star collisions are incredibly rare. But what about the galaxies themselves? What will this grand merger truly look like? And what will become of our familiar night sky? The collision won't be a sudden, catastrophic smash. Instead, it will be a prolonged gravitational dance spanning billions of years. Imagine two colossal swirling clouds of dandelion seeds slowly approaching each other. Initially, their outer edges will begin to feel each other's gravitational pull, distorting their shapes. Andromeda, being the more massive of the two, will exert a stronger gravitational influence, likely pulling on our Milky Way's spiral arms, stretching them out into long tidal tails of stars and gas. Then will come the first pass-through. The galaxies will thread through each other, their vast dark matter halos merging, and the stellar disks interpenetrating. During this phase, the gravitational forces will be intense, stirring up the gas and dust within both galaxies, triggering spectacular bursts of star formation. The night sky from Earth, if humanity were still around, would be utterly transformed. We might see new, brilliant clusters of stars ignite across the sky, and the magnificent spiral arms of Andromeda would loom ever larger, eventually filling huge swaths of our celestial sphere, a breathtaking, terrifying spectacle. After this initial pass, the galaxies won't immediately settle. Their mutual gravitational attraction will pull them back together for another pass, perhaps several more, each time stripping away more stars and gas, flinging some out into intergalactic space, while others fall into the newly forming combined galactic core. This gravitational back and forth will continue for a couple of billion years, gradually disrupting their elegant spiral structures. Eventually, the two galaxies will coalesce into a single, much larger, more spherical entity. The distinct spiral arms will be gone, replaced by a more diffuse, elliptical shape. This new galaxy, affectionately dubbed Milkomeda or Milkdromeda by astronomers, will likely be a giant elliptical galaxy, its stars orbiting in more random, less organized paths. The intense star formation triggered by the collision will eventually subside, and the new galaxy will be dominated by older, redder stars, glowing with a more sedate ancient light. And what of our solar system amidst this colossal transformation? While the night sky will be unrecognizable, our sun and its planets are statistically very unlikely to be directly impacted. The distances between stars are simply too immense. Our solar system might be flung into a new orbit, perhaps even into the outer reaches of the newly formed Milkomeda, or even, though less likely, ejected into intergalactic space. But the planets themselves and the sun will remain intact. The biggest change will be our cosmic address and the awe-inspiring, ever-changing view from our planetary perch. It's a future that is both violent and beautiful, a testament to the dynamic, ever-evolving nature of the universe. We left off with our solar system, safe from direct stellar collisions, yet destined for a grand orbital reshuffle within the newly formed Milkomeda. Think about that for a moment. Our sun, our Earth, our entire cosmic neighborhood, caught in a gravitational waltz spanning billions of years, dancing to the tune of two merging titans. It's a spectacular thought, isn't it? But it also brings us face to face with one of the most profound paradoxes of the universe, something that truly illuminates how big the Andromeda Galaxy, and indeed all galaxies, really are: the sheer overwhelming emptiness of space. We've talked about Andromeda's incredible span, 220,000 light-years from edge to edge, housing 1 trillion stars. 1 trillion. That sounds like a crowded metropolis, doesn't it? Like every square inch must be bursting with celestial bodies. And yet, when the Milky Way and Andromeda meet, the chances of even two stars actually crashing into each other are infinitesimally small, vanishingly close to zero. How can that be? How can something so vast, so star-studded, still be so empty? This, my friends, is where our human intuition, honed by terrestrial experiences, completely breaks down. Imagine our Sun, a star so immense it contains 99.2% of the mass of our entire solar system. Now, picture it as a single grain of sand. If the Sun were a grain of sand, how far away do you think the next nearest star, Proxima Centauri, would be? On a human scale, you might guess a few inches, maybe a foot, perhaps a few miles if you're thinking big. Try this. If the Sun were a grain of sand, Proxima Centauri would be another grain of sand, 4 miles away. 4 miles? And that's just our closest neighbour. The space between stars is truly staggering, an abyss of vacuum that utterly dwarfs the stars themselves. Galaxies aren't dense clusters of stars packed shoulder to shoulder. They are vast, intricate tapestries woven from billions upon billions of individual points of light, each separated by unfathomable gulfs of nothingness. When Andromeda and the Milky Way collide, it's not like two swarms of bees smashing into each other. It's more like two incredibly diffuse clouds of dandelion seeds passing through one another, with the occasional rare gravitational nudge, causing a slight change in trajectory for a few unlucky seeds. It's this profound emptiness that allows for the graceful, slow-motion ballet of galactic mergers. The stars themselves sail past each other, largely untouched, their individual fates mostly determined by the collective gravitational pull of the entire system. And what precisely is that collective gravitational pull mostly made of? Now we get to one of the universe's greatest mysteries, and a fundamental component of Andromeda's true bigness. Dark matter. Remember how we mentioned Andromeda's total mass is estimated at 1.5 trillion solar masses? That's a staggering number. But here's the kicker. If you add up all the mass from Andromeda's trillion stars, its gas, its dust, its nebula, its planets, its black holes, everything we can see with our telescopes, everything that interacts with light, you only account for a tiny fraction of that 1.5 trillion, maybe 10 to 15% at most. The vast majority of Andromeda's mass, well over 85%, comes from something utterly invisible, something we call dark matter. Dark matter. It sounds like something out of a science fiction novel, doesn't it? And in many ways it's more mysterious and fantastical than any fiction. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact with the electromagnetic force at all, which means it's completely transparent, utterly undetectable by any of our light-based instruments. You could be staring directly at a massive clump of dark matter, and you wouldn't see a thing. It's truly dark. So if we can't see it, how do we know it's there? The answer, as is so often the case in astronomy, lies in gravity. We observe galaxies like Andromeda spinning at incredible speeds. If their visible matter, their stars and gas, were all there was, these galaxies would simply fly apart. The centrifugal force generated by their rotation would overcome the gravitational pull of their visible components, and poof! No more spiral arms, no more organized galactic structures. Yet they don't fly apart. They hold together, beautifully, majestically. This tells us there must be a tremendous amount of unseen mass, exerting a powerful gravitational tug holding everything in place. That unseen, gravitationally dominant component is dark matter. Imagine a giant, invisible sphere, a colossal dark matter halo enveloping Andromeda. This halo extends far beyond the visible disk of stars, stretching out to perhaps 10 times the diameter of the luminous galaxy itself. It's like a colossal ethereal scaffolding providing the gravitational backbone for the entire structure. Andromeda's visible stars and gas are merely a sparkling jewel suspended within this much larger, invisible gravitational well. This dark matter halo is where the bulk of that 1.5 trillion solar masses resides. It's what gives Andromeda its immense gravitational reach, its powerful pull that's currently tugging the Milky Way closer and closer. This isn't just a quirk of Andromeda. Every large galaxy we observe appears to be embedded in its own dark matter halo. It's the cosmic glue, the invisible architect of the universe on galactic scales. Without dark matter, galaxies as we know them simply wouldn't exist. They wouldn't have formed in the first place, or if they did, they would have long since dispersed into the void. So when we ask, how big is the Andromeda Galaxy really? The answer goes far beyond the 20,000 light-years of its visible stellar disk. It's also defined by the immense invisible dark matter halo that stretches for perhaps 2 million light-years across, making it a truly colossal gravitational entity. This invisible bigness is what orchestrates the grand cosmic dance, what keeps the stars in their orbits, and what ensures that our future encounter with Andromeda will be a slow gravitational embrace rather than a chaotic, destructive crash. The collision of Andromeda and the Milky Way, then, is primarily a collision of these two colossal dark matter halos. They will be the first components to truly interact, passing through each other, their invisible gravitational fields distorting and reshaping each other long before the stars even begin to feel the collective pull. This interaction will be a slow, drawn-out process, spanning billions of years, a testament to the leisurely pace of cosmic events. And let's zoom out even further. This isn't a unique event, this galactic merger. Oh no, the universe is a dynamic, ever-changing place, and galactic collisions are a fundamental part of its evolution. Galaxies grow by merging, by cannibalizing smaller neighbors, by gravitationally attracting and absorbing other cosmic islands. The Milky Way itself bears the scars and echoes of past mergers, faint streams of stars in our halo that are remnants of smaller galaxies we've absorbed over billions of years. Andromeda, with its intriguing double nucleus, likely carries the signature of a past merger too, a smaller galaxy swallowed whole, its core settling within Andromeda's own. Think of the spectacular antennae galaxies. Two spiral galaxies in the process of a dramatic head-on collision, their forms utterly distorted, their spiral arms ripped into long curving tails by immense tidal forces. These galaxies are currently experiencing an incredible burst of star formation, triggered by the compression of gas clouds as the galaxies interact. It's a preview, in fast forward, of what our future night sky might look like during the early stages of the Milky-Way merger. Our skies, currently dotted with serene distant points of light, will one day be filled with vast, glowing nebulae, brilliant blue star-forming regions, and the visible expanding disks of two galaxies engaged in their final beautiful embrace. Ultimately, as we've discussed, Milky Way will settle into a new, more stable configuration. The original spiral structures will be largely erased, the graceful arms unwound and stretched, the stars settling into more random, elongated orbits around a common centre, the result will be a giant elliptical galaxy. These are the largest galaxies in the universe, often formed from the mergers of multiple spirals, characterized by their smooth, featureless football-like shapes and their generally older, redder stellar populations. They are the cosmic behemoths, the gravitational anchors of their galaxy clusters. Milky Way will become one of these, a majestic elliptical, a testament to the universe's constant cycle of creation and destruction, growth and transformation. So when we look up at the night sky and find that faint, fuzzy patch of light that is the Andromeda Galaxy, we're not just seeing a collection of 1 trillion stars 2.5 million light-years away. We're seeing the visible tip of an immense, invisible iceberg of dark matter, the gravitational engine of a cosmic giant. We're seeing a galaxy that is not only vast in its visible extent, but even vaster in its unseen gravitational influence. We're seeing a future dance partner, a cosmic destiny woven into the very fabric of space and time. And this understanding, this ability to peer beyond the visible, to deduce the presence of the unseen, to predict events billions of years in the future based on the subtle whispers of gravity, that, perhaps, is the most profound revelation of all. It reminds us that our universe is far richer, far more complex, and far more astonishing than our immediate senses could ever convey. The question, how big is the Andromeda Galaxy really, isn't just about measurement. It's about expanding our very conception of reality, pushing the boundaries of what we can imagine, and embracing the magnificent invisible grandeur of the cosmos. And it's an adventure we've only just begun. And so we stand at the precipice of an unimaginable future, gazing across 2.5 million light-years and 4.5 billion years into an event that will redefine our cosmic home. We've established that the Milky Way and Andromeda are on a collision course, destined to merge into a magnificent new entity we affectionately call Milky Way. But what precisely does this gravitational ballet entail? What will it look like? What will it feel like if we could somehow fast forward time and be there to witness it? Let's journey into that future, shall we? Let's trace the intricate steps of this cosmic dance, from the first tentative approach to the grand final embrace. Imagine, if you will, the vast, inky blackness of space, studded with the familiar constellations. For billions of years, Andromeda has been a faint, fuzzy smudge, a distant, ethereal glow in our night sky. But as the eons tick by, that smudge begins to grow. Slowly, imperceptibly at first, then with an accelerating grandeur. It's not a sudden, dramatic rush, mind you. This is a cosmic ballet, played out on timescales that dwarf human comprehension. The first real signs of the impending merger will appear when Andromeda is still a good distance away, perhaps 1 million years before the actual first pass. What you'll see, or rather what future inhabitants of Earth will see, is Andromeda expanding in the night sky. From a faint oval it will morph into a truly spectacular sight, its spiral arms becoming distinct, its brilliant core a beacon. It will eventually span an area several times the apparent width of our own moon, a breathtaking celestial spectacle, dominating the night sky in a way no other object does today. Imagine looking up and seeing another entire galaxy, its countless stars glittering, its nebulae glowing stretched across the heavens. It will be a sight to inspire awe, wonder, and perhaps a touch of existential contemplation. Then comes the first true pass. This isn't a head-on collision, as we might picture two cars smashing together. Oh no, the universe is far more elegant than that. Think of it more like two immensely heavy, gravitationally bound ships passing in the night, their wakes creating ripples that extend far beyond their immediate presence. our galaxies, pulled by each other's immense gravity, will begin to distort. Picture this: the Milky Way, our beautiful spiral, and Andromeda, its even grander counterpart, are both encased in those colossal invisible halos of dark matter we discussed. These halos are the true protagonists of the initial encounter. As they interpenetrate, their combined gravitational fields will begin to stretch and pull at the visible matter, the stars, the gas, the dust, within both galaxies. It's like stretching a piece of taffy or watching the ocean tides respond to the moon's pull, but on a galactic scale. Gigantic tidal forces will rip through both structures. Our spiral arms, once so pristine and ordered, might begin to unravel, pulled into long, looping streams of stars and gas. Andromeda will experience a similar fate. These tidal tails, magnificent streamers of cosmic material, will stretch out into intergalactic space, a testament to the colossal forces at play. It will be a period of immense disruption, but also one of incredible beauty. And here's where the fireworks truly begin. When these vast clouds of gas and dust, normally spread out, are compressed by the gravitational shockwaves of the colliding galaxies, they collapse. And what happens when gas clouds collapse? They ignite. This compression will trigger spectacular bursts of star formation. Entire stellar nurseries, dormant for eons, will suddenly light up, giving birth to millions upon millions of new stars. The galaxies, for a time, will blaze with an unprecedented brilliance, a cosmic celebration of creation amidst the chaos. The night sky will be a canvas of brilliant blue-white young stars, nebulae glowing fiercely, and the dramatic, arcing streams of distorted galactic matter. This isn't a one-and-done event. Oh no, this is a dance with multiple steps. After their first majestic pass, the two galaxies, still bound by their mutual gravity, will swing away from each other, like cosmic partners in a grand waltz. But they won't escape. Their momentum will carry them outward for billions of years, only to be reeled back in by the irresistible pull of gravity. They will perform this intricate pas de deux several times, each pass bringing them closer, each pass increasing the distortion, each pass triggering more bursts of star formation. With every gravitational embrace, the distinct spiral structures that define the Milky Way and Andromeda today will become increasingly scrambled. The elegant arms, the organized disks, they will slowly, inexorably be erased. Imagine stirring two different colored paints together. Initially, you see distinct swirls, but eventually they blend into a new, uniform hue. That's what will happen to our galaxies. The gas and dust will be flung about, the stars redistributed, until the original forms are almost unrecognizable. Finally, after billions of years of this gravitational tango, the two galaxies will truly coalesce. Their cores, each harboring a supermassive black hole, will eventually spiral inward towards each other. This too will be a slow, drawn-out process, involving gravitational friction and the slingshotting of stars. But eventually those two titanic black holes will merge, forming a single, even more colossal, supermassive black hole at the heart of the newly formed Milkomeda. And what kind of galaxy will Milkomeda be? It won't be a spiral like its parents. No, the violent gravitational interactions will have thoroughly disrupted the delicate disks and spiral arms. Instead, Milkomeda will be a giant elliptical galaxy. Elliptical galaxies are very different beasts from spirals. They tend to be much more spheroidal or ellipsoidal in shape, lacking the distinct arms. They are often characterized by older, redder stars because much of their gas and dust has been either used up in massive star formation bursts during the merger or ejected into intergalactic space. So the brilliant blue-white young stars that lit up the skies during the initial passes will eventually fade, replaced by a more sedate reddish glow from the older, longer-lived stars. Milky will be a majestic, diffuse, somewhat featureless cosmic behemoth, a testament to the ultimate triumph of gravity. Now, let's bring this back home for a moment. What about our solar system? What about Earth? We've already established that direct stellar collisions are incredibly unlikely. The vastness of space between individual stars is truly mind-boggling. Even when two galaxies merge, it's mostly empty space passing through empty space. Think of two flocks of birds flying through each other. Individual birds rarely collide. However, our solar system will certainly not emerge unscathed from this gravitational maelstrom. While our Sun and its planets will remain intact, our orbit within the new galaxy will be dramatically altered. We might find ourselves flung into a new neighbourhood, perhaps much further from the galactic core than we are today, or perhaps closer. Our Sun will be gravitationally reshuffled, much like a card being dealt into a new hand. Imagine the night sky from Earth, billions of years from now, looking out from within this new Milky Way. The familiar band of the Milky Way, our own home galaxy, will be gone. The distinct spiral of Andromeda will be gone. Instead, the sky will likely be filled with a more uniform, diffuse glow of billions of stars, perhaps denser in some regions than others, but without the defined structure we see today. The new galactic core, with its colossal merge black hole, might be a brilliant, overpowering beacon. The constellations we know today will still be there, but they will be set against a dramatically different backdrop, one that speaks of a profound cosmic transformation. And what happens after Milky Way forms? Does the story end there? Of course not. The universe is a dynamic, ever-evolving entity. Milky Way itself will continue to evolve, slowly consuming smaller satellite galaxies, its stars aging, its gas reserves dwindling. Over truly immense timescales, even Milky Way might eventually merge with other galaxies in the Virgo supercluster, gradually building up even larger structures. Ultimately, the long-term fate of Milky Way, and indeed of all galaxies, is tied to the grand, overarching story of the universe itself. The accelerating expansion of the universe, driven by that mysterious force we call dark energy, means that eventually the vast cosmic distances between galaxy clusters will grow so immense that even the light from distant galaxies will never reach us. Milky Way might one day be an isolated island universe in an otherwise empty, ever-expanding void, but that is a story for billions, perhaps trillions, of years from now. For now, what we understand about the impending collision of the Milky Way and Andromeda is a testament to humanity's insatiable curiosity and our incredible scientific prowess. It is a story of immense scales, of invisible forces, and of a future that, while far off, is as inevitable as the rising sun. It reminds us that our place in the cosmos is not static. We are not just passengers on a small blue marble. We are participants in a grand, ongoing cosmic drama. The universe is alive, it is changing, and it is far more wondrous and dynamic than we could ever truly imagine. And the next time you look up at that faint, fuzzy smudge that is Andromeda, remember, you are not just looking at a distant galaxy, you are looking at our future home, a future that is already in motion, billions of years in the making. What an astonishing thought, isn't it? What an utterly breathtaking, mind-bending reality. So we've journeyed through the vastness, witnessed the inevitable embrace of Andromeda and the Milky Way, and peered into the future to behold Milkomeda, our new galactic home. This colossal elliptical galaxy, born from a cosmic dance spanning billions of years, represents a new chapter in our corner of the universe. But what does it truly mean for Milkomeda to settle into this new identity? And how does its immense size compare to the even grander tapestries woven across the cosmos? Imagine Milkomeda, billions of years from now, a majestic, somewhat serene giant. Gone are the dramatic swirling arms of its spiral predecessors. Instead, we see a more uniform spheroidal distribution of stars, older and predominantly redder, like embers glowing steadily after a roaring fire has settled. This is the hallmark of a giant elliptical galaxy, a place where star formation has largely tapered off, the gas and dust largely consumed or dispersed during the violent merger. It's a stable, gravitationally robust entity. Its immense mass, much of it still unseen dark matter, holding it together with an unbreakable grip. The dark matter, our silent cosmic architect, continues its crucial work. It was the dark matter halos that first touched, initiating the gravitational tug-of-war that reshaped the galaxies. And it is the dark matter that will continue to provide the deep gravitational well, the invisible scaffolding ensuring Milkomeda's long-term stability. Without it, the stars, even in this new elliptical configuration, would simply fly apart, unable to maintain their cohesion against the centrifugal forces of their orbits. Milkomeda, in essence, is a monument to dark matter's pervasive and foundational influence. But Milkomeda isn't just a solitary behemoth in the vast expanse. It will become the undisputed gravitational anchor of what we currently call the local group, our small cluster of gravitationally bound galaxies. Right now, this group includes our Milky Way Andromeda, the Triangulum Galaxy, M33, and dozens of smaller dwarf galaxies like the Magellanic Clouds. As Milkomeda forms and stabilizes, its immense gravitational pull will dominate this entire region. What happens to those smaller galaxies then? Well, the cosmic dance isn't over. It merely evolves. The Triangulum Galaxy, for instance, is currently the third largest member of our local group, and it's actually gravitationally bound to Andromeda right now, orbiting it. In the future, as Andromeda merges with the Milky Way, Triangulum will likely be pulled into the fray. It might even perform its own smaller, graceful merger with the nascent Milkomeda, contributing its own stars and gas to the growing supergalaxy. Many of the other dwarf galaxies too will eventually be absorbed, their stars becoming part of Milkomeda's vast halo, much like tiny streams feeding into a colossal river. So Milkomeda won't just be the combined mass of Andromeda and the Milky Way, it will be the eventual gravitational devourer of most, if not all, of the other galaxies in our local group. It will become a true galactic titan, a singular dominant entity in our local cosmic neighborhood. When we ask, how big is Andromeda really, we realize its future self, Milkomeda, will be even grander, a testament to the continuous process of galactic growth through accretion and merger. But even Milkomeda, for all its future glory, is just one player on an infinitely larger stage. Our local group, with Milkomeda at its heart, is merely a tiny speck within a much, much larger structure, a galaxy cluster. Imagine our local group as a small, isolated town. Then imagine that town is part of a much larger metropolitan area, a sprawling city of galaxies. That's a galaxy cluster. The closest such city to us is the Virgo cluster, located about 54 million light-years away. It's an astonishing collection of over 300 and possibly up to 2,000 galaxies. Think about that for a moment. Thousands of galaxies, each potentially containing hundreds of billions or even trillions of stars, all bound together by gravity, swirling and interacting within a region of space millions of light years across. The Virgo cluster is roughly 10 million light years wide, making it vastly larger and more massive than our entire local group. Our local group, in fact, is just a small, relatively sparse outpost on the outskirts of this much more massive structure. Now, if a galaxy cluster is a city, what comes next? You guessed it, a supercluster. Superclusters are the largest known structures in the universe, true cosmic continents. They are groups of galaxy clusters and galaxy groups, all loosely bound together by gravity, stretching across hundreds of millions of light years. Our local group, along with the Virgo cluster and many other galaxy clusters and groups, is part of a truly immense structure we call the Laniakea supercluster. Laniakea, whose name means immense heaven in Hawaiian, is mind-bogglingly vast. It spans approximately 520 million light-years across and contains the mass of about 100 million billion suns. Within Laniakea, there are roughly 100,000 galaxies, organized into a complex web of filaments and nodes. Our local group, and by extension the future Milkomeda, is slowly but surely being pulled towards a massive gravitational center within Laniakea, an area known as the Great Attractor. This region contains a massive concentration of matter, so powerful that it pulls entire galaxy clusters, including our own, towards it. So when we ask, how big is Andromeda really? The answer continuously expands. It's not just 220,000 light-years across, it's a galaxy destined to become Milkomeda, a dominant force in our local group. And that local group, in turn, is a tiny suburb within the immense Virgo cluster. And the Virgo cluster is but one of many clusters within the sprawling Laniakea supercluster. This hierarchical structure, from individual stars to galaxies, to groups, clusters and superclusters, isn't just a random arrangement. It's the direct result of gravity acting on the matter distributed throughout the universe since the Big Bang. Over cosmic timescales, tiny initial density fluctuations in the early universe, amplified by the relentless pull of dark matter, grew into these magnificent structures. The dark matter formed the initial gravitational seeds, drawing in the ordinary luminous matter, stars, gas, dust, to form galaxies, which then clustered together. This grand cosmic architecture, often referred to as the cosmic web, paints a picture of a universe that is far from uniform. Instead, it's a vast, intricate network, like a gigantic glowing spiderweb. Galaxies and clusters of galaxies are concentrated along the filaments of this web, while immense, relatively empty regions called voids lie between them. Imagine the universe not as a uniform soup, but as a sponge, with dense regions and vast empty spaces. Milkomeda, the future behemoth of our local group, will be one of countless shining knots along one of these cosmic threads. The universe, then, is a place of continuous dynamic evolution. From the dance of two galaxies forming Milkomeda, to the slow gravitational infall of entire galaxy clusters towards the Great Attractor, to the ongoing expansion of the universe itself, everything is in motion, everything is changing. Our perspective, often limited to the human scale of time and distance, struggles to grasp these truly astronomical dimensions and durations. But that's precisely why we explore these concepts, isn't it? To stretch our minds, to expand our understanding of our place in the cosmos. Andromeda, a galaxy we can see with the naked eye on a clear night, is not just a distant smudge of light. It's a mirror reflecting our own galactic future, a testament to the unseen forces shaping the universe, and a gateway to understanding the truly colossal structures that make up the vast, intricate, and ever-evolving cosmic web. the question, how big is Andromeda really, morphs from a simple query about size into a profound exploration of connection, evolution, and the boundless scale of existence itself. And the journey, as always, continues. We've journeyed through the vastness of Andromeda, witnessed its grand collision with our own Milky Way, and even imagined the birth of Milkomeda, the future super galaxy that will dominate our local group. We've seen how gravity, that fundamental sculptor of the cosmos, binds stars into galaxies and galaxies into clusters, weaving the intricate tapestry we call the cosmic web. But as we peer further into this grand design, we encounter two of the most profound, enigmatic mysteries of the universe: dark matter and dark energy. These aren't just obscure footnotes. They are the invisible architects and drivers of the cosmos, shaping everything from the spin of a galaxy to the ultimate fate of all existence. Remember how we discussed that over 85% of Andromeda's mass, and indeed the mass of all large galaxies, is made of something we can't see, something we call dark matter. It's the invisible scaffolding, the gravitational glue that holds galaxies together, preventing them from flying apart as they spin at incredible speeds. If we could only see the stars and gas in Andromeda, it simply wouldn't have enough mass to generate the gravitational pull needed to maintain its structure. It would be like trying to keep a spinning top together with only a fraction of the material it needs. It would just dissipate. So, what? This elusive dark matter. That, my friends, is one of the biggest questions in modern astrophysics, and it's a question that keeps countless brilliant minds awake at night. We know what it isn't. It isn't ordinary matter, the protons, neutrons, and electrons that make up you, me, the Earth, the stars and the galaxies we can see. It doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation, which is why it's dark. It's not just dust clouds or unlit planets, because those would still interact with light to some degree, or we'd detect their gravitational lensing effects in different ways. Our evidence for dark matter is purely gravitational. We infer its presence from its effects on visible matter. Think of it like this. Imagine you're watching a marionette show, but you can't see the puppeteer. You see the puppets moving, dancing, interacting, in ways that suggest an unseen force is manipulating them. That unseen force is dark matter. We see galaxies rotating faster than they should based on their visible mass, galaxy clusters holding together despite their immense speeds, and light bending around massive objects in ways that visible matter alone cannot explain, a phenomenon called gravitational lensing. The early universe, as mapped by the cosmic microwave background, CMB radiation, also shows patterns that only make sense if dark matter was present from the very beginning, acting as the gravitational seeds for the first structures. Scientists have proposed various candidates for dark matter. Perhaps it's composed of exotic particles that we haven't yet discovered. Particles that interact very weakly with normal matter, leading to the name weakly interacting massive particles, or WIMPs. These hypothetical particles would pass right through us, through the Earth, through stars, almost without a trace. Or perhaps it's something even more exotic, like actions. Extremely light particles that are still purely theoretical. Another idea, though largely discounted now, was that dark matter could be made up of macrosets, massive compact halo objects, like black holes, neutron stars, or brown dwarfs, but not enough of these have been detected to account for the missing mass. The truth is, we don't know yet, but the search is on, with experiments deep underground trying to detect WIMPs and observatories scanning the skies for gravitational lensing effects. Whatever dark matter turns out to be, its sheer abundance is staggering. It forms these immense ethereal halos around galaxies, extending far beyond the visible starlight. When Andromeda and the Milky Way begin their dance, it's these vast dark matter halos that will be the first to interact, feeling each other's gravitational pull long before any stars even notice a change. Their initial collision will be a silent, invisible embrace of gravity, tugging and distorting, setting the stage for the dramatic cosmic ballet that follows. But dark matter, as mysterious and pervasive as it is, only accounts for about 27% of the total mass energy content of the universe. The vast majority, an astonishing 68%, is something even more baffling. Dark energy. If dark matter is the invisible glue that pulls things together, dark energy is the invisible force that pushes everything apart, and it's doing so at an ever-accelerating rate. For centuries, astronomers believed that the expansion of the universe, set in motion by the Big Bang, would gradually slow down due to the collective gravity of all matter. It made intuitive sense, right? Like a ball thrown into the air, gravity should eventually pull it back down, or at least slow its ascent. Then in the late 90s, observations of distant Type Ia supernova delivered a shocking revelation. These supernovae, which act as another type of standard candle, remember Henrietta Swan-Leavitt and Cepheids, consistently appeared fainter than they should have been for their measured redshift. This meant they were much farther away than expected, implying that the universe's expansion wasn't slowing down at all, it was speeding up. Imagine throwing that ball into the air, and instead of slowing down, it starts accelerating upwards, faster and faster, defying all expectations. That's what dark energy is doing to our universe. Dark energy is not a traditional force like gravity. It's thought to be an intrinsic property of space itself, a kind of anti-gravitational pressure that arises as new space is created. As the universe expands, more space is created, and therefore more dark energy comes into existence, further accelerating the expansion. It's a runaway process, and its implications are truly mind-boggling. What will this accelerating expansion mean for Milkomeda, our future galactic home? In the grand scheme of things, Milkomeda will be a stable, gravitationally bound entity, a magnificent island of stars within the local group. But the local group itself, along with all other galaxy groups and clusters, is embedded in a universe dominated by dark energy. As billions upon billions of years tick by, the accelerating expansion will drive other galaxy clusters further and further away from us, faster than the speed of light, eventually pushing them beyond our cosmological horizon. Imagine Milkomeda shining brightly, but as time progresses, all the other galaxies in the universe will recede from view. Our descendants, if they still exist, might one day look out into the night sky and see only Milkomeda, alone in a vast, empty cosmic ocean. The light from distant galaxies will become so stretched by the expansion of space that it will redshift out of existence or simply never reach us. Eventually, the universe outside our local group will become utterly invisible, silent, and unreachable. Milkomeda will be an isolated island, unaware of the immense cosmic tapestry that once surrounded it. This is one of the potential fates of the universe, often called the Big Freeze, or heat death, where the universe simply expands forever, becoming increasingly cold, dilute, and empty. The alternative, if dark energy were to increase in strength, is even more dramatic: the Big Rip. In this terrifying scenario, the accelerating expansion would eventually become so powerful that it would overcome all gravitational forces, first ripping apart galaxy clusters, then individual galaxies like Milkomeda, then stars, planets, and finally even atoms themselves. Everything would be torn apart into its fundamental constituents, but current observations suggest this is less likely. The Big Freeze seems to be the more probable long-term future. So when we ask, how big is the Andromeda Galaxy really, we're not just measuring its diameter in light years or counting its stars. We're also asking about its place in an expanding, evolving universe. A universe where the visible matter we know makes up only a tiny fraction of the cosmic recipe. Andromeda, with its trillion stars, its magnificent spiral arms, and its immense dark matter halo, is a testament to the power of gravity. But its journey, and our own, is ultimately governed by these two profound unknowns: dark matter, the invisible scaffold, and dark energy, the accelerating engine of the cosmos. The universe, my friends, is far stranger and more wonderful than we could ever have imagined. Our quest to understand Andromeda has led us to the very edge of our knowledge, opening doors to mysteries that challenge our most fundamental assumptions about reality. We have come to appreciate that the cosmos is not just a collection of objects, but a dynamic, interconnected system, constantly changing, constantly expanding, and constantly inviting us to look deeper, to question more, and to marvel at the sheer breathtaking scale of it all. What new discoveries await us as we continue to probe these cosmic enigmas? Only time and the relentless pursuit of knowledge will tell. And isn't that just the most exciting thought imaginable? We've journeyed through the vastness of Andromeda, charted its impending collision with our own galaxy, and even peered into the distant future of Milkomda, our cosmic merger. We've witnessed the dance of gravitational forces, the birth of stars, and the grand, slow waltz of galactic evolution. But as we stand at the precipice of these grand cosmic narratives, two colossal unknowns loom largest, shaping everything we've discussed and defining the very fabric of our universe: dark matter and dark energy. You see, for all the brilliant light that galaxies like Andromeda pour into the cosmos, for all the trillions of stars and nebulous clouds we can observe, what we can't see holds the ultimate sway. These invisible components are not just minor footnotes, they are the fundamental architects and drivers of the universe, dictating everything from the formation of the first galaxies to the ultimate fate of Milkomda. Let's first grapple with the enigma of the dark matter. Imagine, if you will, that you're watching a cosmic ballet. You see the dancers, the stars, the gas, the dust, twirling and turning with incredible speed. Now, if you were to calculate the gravitational pull these visible dancers exert on each other, based on their observed mass, you'd find something truly puzzling. They should be flying apart. The galaxies, especially the spiral ones like Andromeda and the Milky Way, spin so rapidly that their outer edges ought to be flung off into intergalactic space, much like water droplets from a spinning top. But they aren't. They hold together, stubbornly defying our initial calculations. This cosmic paradox led astronomers, most notably the brilliant Vera Rubin in the 1960s and 70s, to a startling conclusion. There must be far more mass in galaxies than we can see. Something invisible, something that doesn't emit, absorb, or reflect light, is providing the extra gravitational glue. We affectionately, or perhaps a little mystifiedly, call this missing mass or dark matter. How much are we talking about? It's not a small correction, my friends. Dark matter makes up about 27% of the universe's total mass energy content. Compare that to the paltry 5% that constitutes all the normal matter we can see and interact with. Every star, planet, gas cloud, and even you and me. Think about that for a moment. 85% of the mass of a galaxy, including our Andromeda neighbour, is composed of this mysterious unseen substance. So when we talk about Andromeda's immense size and its gravitational dominance, we're not just talking about its trillion stars, we're talking about its colossal dark matter halo, a vast spherical shroud of invisible mass that extends far beyond its visible stellar disk. This halo is the true gravitational anchor, the scaffolding upon which the luminous galaxy is built. It's what keeps Andromeda's outer stars from escaping its embrace, and it's what gives it the gravitational heft to embark on its collision course with the Milky Way. Remember our discussion about the collision? We emphasised that the first components to interact would be these dark matter halos. It's not a direct impact of stars, but a slow gravitational grappling match between these invisible behemoths. Their mutual gravitational pull, largely driven by dark matter, will begin to distort and stretch the spiral arms of both galaxies long before any stars get close. It's a dance choreographed by the unseen. But what is dark matter? There's the million light-year question. We know what it does, but not what it is. Scientists have proposed various candidates, from exotic particles like WIMPs, weakly interacting massive particles, to primordial black holes. Experiments deep underground and in particle accelerators around the world are tirelessly searching for direct evidence, hoping to catch a fleeting interaction of a dark matter particle with our detectors. It's like trying to catch a ghost, but a ghost that weighs down entire galaxies. The search continues, a testament to humanity's relentless curiosity. If dark matter is the unseen architect that holds things together, then dark energy is the enigmatic force tearing the universe apart. Now, this is where things get truly mind-bending. For decades, astronomers believed that the expansion of the universe set in motion by the Big Bang must be slowing down due to the mutual gravitational pull of all matter within it. It made sense, right? Gravity pulls, so expansion should decelerate. But then came the late 90s, and a series of groundbreaking observations of distant supernovae, exploding stars that act as powerful standard candles for measuring cosmic distances. What these observations, led by teams including Saul Perlmutter, Adam Rees, and Brian Schmidt, who later shared a Nobel Prize for their discovery, revealed was utterly shocking. The expansion of the universe isn't slowing down, it's accelerating. Imagine throwing a ball into the air, expecting it to slow down and fall back to Earth, only to watch it speed up and vanish into the sky. That's essentially what astronomers witnessed on a cosmic scale. Some unknown force is actively pushing the fabric of space-time apart, overcoming the attractive force of gravity. We call this mysterious pervasive force dark energy. Dark energy is even more dominant than dark matter, comprising about 68% of the universe's total mass energy content. Think of it. 95% of our universe is made of stuff we can't see and don't fully understand. It's a humbling thought, isn't it? Unlike dark matter, which clumps around galaxies and clusters, dark energy seems to be uniformly distributed throughout space. It's like an inherent property of space itself, an invisible spring embedded in every cubic centimetre of the cosmos, constantly pushing outwards. This relentless push is the driving force behind the accelerating expansion of the universe. And this, my friends, brings us back to the ultimate fate of Milky, our future super galaxy. Remember how we discussed the Big Freeze and Milky becoming an isolated island universe? That future is directly dictated by dark energy. As the universe continues to expand at an ever-increasing rate, distant galaxy clusters will recede from us faster and faster, eventually crossing a cosmic horizon beyond which their light will never reach us. they will effectively become invisible, unreachable, and ultimately unknowable. Milky, along with the other galaxies in our local group that it will eventually absorb, will be gravitationally bound, a magnificent island in an ever-expanding ocean of emptiness. The cosmic web, that grand filamentary structure of galaxies, will stretch and thin out, leaving our local supergalaxy increasingly alone in the vast cosmic void. Future inhabitants of Milky, billions of years from now, might look out into a night sky devoid of other galaxies, completely unaware of the rich, diverse universe that once surrounded them. The accelerating expansion driven by dark energy will have effectively erased them from our view, leaving us in splendid but profound isolation. So when we gaze upon Andromeda, that fuzzy patch of light 2.5 million light-years away, we're not just seeing a collection of stars, we're looking at a profound interplay of these invisible forces. Andromeda's immense dark matter halo is pulling it towards us, orchestrating the grand collision. Simultaneously, the dark energy permeating the space between us and other more distant galaxies is pushing them away, ensuring that Milky's grand merger will eventually lead to a singular, isolated cosmic destiny. The study of Andromeda then becomes a lens through which we can explore these deepest cosmological mysteries. Its motion, its structure, its future are all intrinsically linked to the presence and properties of dark matter and dark energy. By observing and modelling Andromeda, we gain crucial data points in our attempt to understand these fundamental components that constitute the vast majority of our universe. We know what they do, these dark forces. We've mapped their effects, calculated their proportions, and even predicted their long-term consequences. But the greatest mystery of all remains. What are they? What fundamental particles or properties of space-time are responsible for these unseen giants? The universe, in its infinite wisdom, continues to hold its most profound secrets close, challenging us to push the boundaries of our understanding, to build ever more sensitive instruments, and to dream up ever more ingenious experiments. Andromeda, our cosmic neighbour, stands as a silent sentinel, a magnificent testbed for our theories, a constant reminder that for all we have learned, the universe still has so many breathtaking revelations in store. The journey to truly understand how big is the Andromeda Galaxy really is, in essence, a journey to understand how big, how complex, and how profoundly mysterious our entire universe truly is. Andromeda, our cosmic neighbour hurtling towards us, destined to become one with our Milky Way. We've journeyed through its immense scale, its trillion stars, its inevitable gravitational dance with our home galaxy, and the majestic future it promises as Milky. But as we discussed, Andromeda isn't just a spectacle of stellar grandeur or a future home. It's a living, breathing laboratory, a cosmic Rosetta Stone for the two most profound, most perplexing mysteries of our universe: dark matter and dark energy. Imagine, if you will, standing at the edge of a vast, uncharted ocean. You can feel the powerful currents, see the massive waves, observe the islands rising from its depths, but the ocean itself, its true composition, its unseen depths, the forces that drive its tides, remains largely hidden. This is our relationship with dark matter and dark energy. We see their effects, we measure their influence, but their true nature. That, my friends, remains one of the universe's most tantalizing secrets. And Andromeda, in its magnificent proximity, offers us an unparalleled opportunity to peer into these hidden depths. Let's begin with dark matter. that ethereal architect of galactic structure, the invisible hand that cradles Andromeda and every other large galaxy in its gravitational embrace. We know it's there because without it, galaxies like Andromeda simply wouldn't hold together. Think about it. Andromeda is spinning. It's a colossal cosmic pinwheel with stars and gas clouds orbiting its centre at incredible speeds. If the only mass present were the stars and visible gas we can observe, the outer regions of Andromeda would be flung off into intergalactic space, much like water droplets spinning off a rapidly rotating bicycle wheel. But they don't. They stay put, held firmly into place. This is where the ghostly presence of dark matter comes in. We infer its existence not by seeing it directly, but by measuring its gravitational pull. Through meticulous observations of Andromeda's rotation curve, how fast stars orbit at different distances from its core, astronomers have charted this invisible influence. They found that stars far from the centre, out in the galaxy's sprawling spiral arms, are orbiting much faster than they should be, based on the visible matter alone. This discrepancy, this cosmic deficit of gravity, is the signature of dark matter. It tells us that Andromeda, like the Milky Way, is not just a dazzling disk of stars, it's enveloped in a colossal spherical halo of invisible dark matter, extending far beyond its visible light, acting as a massive unseen anchor. This halo, we estimate, accounts for over 85% of Andromeda's total mass. Can you imagine that? A galaxy with 1 trillion stars, 220,000 light-years across, yet the vast majority of its substance is utterly invisible to us, detectable only through its gravitational whisper. It's like trying to weigh a house by only counting the light bulbs inside. You'd be missing, well, everything else. Andromeda's dark matter halo is not just a theoretical construct, it's the very scaffolding upon which its visible splendour is built. It dictates its shape, its gravitational dynamics, and profoundly its destiny. When the Milky Way and Andromeda finally begin their grand merger, it won't be a head-on collision of stars initially. Oh no! The first, most significant interaction will be between these colossal, invisible dark matter halos. They will be the cosmic titans that first grapple, exerting immense tidal forces on each other, stretching and pulling the visible matter of both galaxies into spectacular fiery streams of stars and gas. It's a gravitational tug-of-war on a scale almost impossible to fathom, orchestrated by unseen forces. But what is dark matter? Is it made of exotic particles, perhaps weakly interacting massive particles, or WIMPs, that pass through ordinary matter almost entirely undetected? Or is it something else entirely? Scientists around the world are engaged in a monumental quest to detect these elusive particles directly, deep underground in laboratories shielded from cosmic rays, or by searching for subtle gravitational lensing effects, where massive dark matter clumps bend the light from distant galaxies, acting like colossal invisible magnifying glasses. Andromeda, being so close and so massive, offers a prime target for studying these lensing effects, giving us clues to the distribution and lumpiness of its dark matter halo. It's a cosmic detective story, and Andromeda is our star witness. Now let's shift our gaze from the attracting grip of dark matter to the expansive push of dark energy, the force that's not just shaping galaxies but accelerating the very expansion of the entire universe. If dark matter is the unseen glue, dark energy is the invisible propellant, pushing everything apart. The story of dark energy began with a profound surprise. In the late 90s, astronomers were studying distant Type Ia supernovae, exploding stars that act as incredibly reliable standard candles because they all reach roughly the same peak brightness. By measuring how dim these distant supernovae appeared, scientists expected to see that the universe's expansion was slowing down due to the collective gravity of all matter within it. Instead, to their utter astonishment, they found the opposite. The expansion of the universe was accelerating. Imagine throwing a ball straight up into the air. You'd expect it to slow down as gravity pulls it back to Earth, right? Now imagine it suddenly speeding up as it flies higher and higher. That's essentially what astronomers observed with the universe. This unexpected acceleration implies the existence of a mysterious, pervasive force that acts as a kind of anti-gravity, pushing space itself apart. We call it dark energy, and it constitutes an astounding 68% of the universe's total mass energy budget. Yes, 68%. That means all the stars, planets, and galaxies we can see, plus all the dark matter we can infer, make up less than a third of the universe's total contents. Mind-bending, isn't it? So what does this accelerating expansion, driven by dark energy, mean for our future galaxy, Milkomeda? It means that while our local galactic cluster, the local group anchored by More and Milkomeda, will remain gravitationally bound, the rest of the universe will continue to recede from us at an ever-increasing pace. Over trillions of years, as dark energy continues its relentless push, distant galaxies will not only move away, but they will eventually cross a cosmological horizon. They will recede so fast that their light will no longer be able to reach us. Imagine being on a ship in an infinitely expanding ocean. As you sail, the horizon itself moves further and further away, and eventually other ships that were once visible will vanish over that ever-expanding horizon, their light simply unable to catch up to you. This is the fate of Milkomeda. It will become a true island universe, gravitationally isolated, with all other galaxies eventually disappearing from its night sky. Our descendants, countless eons from now, if they still exist, will look out into a universe that appears utterly empty beyond our local group. They will have no way of knowing that billions upon billions of other galaxies once filled the cosmos. They won't even be able to discern that the universe is expanding because the evidence, the receding light of distant galaxies, will be forever beyond their reach. This is the Big Freeze scenario, a cold, dark, and ultimately lonely end for the observable universe. All thanks to the inexorable march of dark energy. Andromeda, in its very existence and its impending merger, offers us a unique perspective on these cosmic leviathans. Its dark matter halo is a tangible, albeit invisible entity that we can map and model, providing crucial data for the ongoing hunt for dark matter particles. Its role in the local group, as the largest member, helps us understand how gravity shapes structure on these scales, even as dark energy tries to tear it all apart. By studying Andromeda's evolution, its past interactions, and its future merger with the Milky Way, we gain insights into the interplay between the attractive force of gravity, amplified by dark matter, and the repulsive force of dark energy. We are, in essence, watching a cosmic drama unfold in slow motion. A drama where the two main characters, dark matter and dark energy, are both invisible, yet profoundly influential. Andromeda isn't just a beautiful celestial object, it's a cosmic canvas upon which the fundamental laws of the universe are painted, a testament to the fact that even in our own galactic backyard, the deepest mysteries of existence are waiting to be unravelled. And as we continue to gaze upon its shimmering light, we are reminded that our understanding of the cosmos, while vast, is still only just beginning. The universe, in its infinite wisdom, continues to hold its most profound secrets close, challenging us to look deeper, to question further, and to forever wonder, what else is out there? beyond the visible, beyond the known. We've journeyed together through the visible splendour of Andromeda, witnessing its colossal shears, its breathtaking number of stars, and its inevitable majestic dance with our own Milky Way. We've peered into the distant future, imagining the birth of Milkomeda, a new cosmic island forged from two. But as we concluded our last chapter, we touched upon the true architects of this cosmic drama, the unseen forces that dictate not just the fate of galaxies, but the very fabric and future of the entire universe. Dark matter and dark energy. These aren't just abstract concepts, you see. They are the fundamental, enigmatic truths that underpin everything we've discussed. They are the invisible hands shaping galaxies, stretching the cosmos, and ultimately defining the destiny of Milkomeda itself. And in this final chapter of our exploration, we're going to delve deeper into these profound mysteries, not just to understand what they are, but to appreciate the incredible scientific quest underway to unravel their secrets and what their existence tells us about our place in the universe. Think about it. We've spent centuries mapping the stars, dissecting light and understanding gravity. Yet the vast majority of our universe, about 95% of it, remains shrouded in darkness, a realm beyond our direct perception. Dark matter, comprising roughly 27% of the universe's mass energy, acts as the gravitational glue holding galaxies together, forming the colossal halos that initiated the cosmic embrace between Andromeda and the Milky Way. Without it, these grand spirals would simply fly apart. Then there's dark energy, an even more bewildering entity making up about 68% of the universe, acting as an anti-gravitational pressure, accelerating the expansion of space itself. So how do we study something that we can't see, touch, or even directly detect? This is one of the grandest challenges in modern astrophysics and particle physics, and it's a testament to human ingenuity. For dark matter, the hunt is on through multiple avenues. Imagine trying to understand the wind by only observing how it rustles the leaves on a tree, or how it pushes a sailboat across the water. We see its effects, but the wind itself is invisible. That's precisely our situation with dark matter. We see its gravitational influence everywhere, in the rotational curves of galaxies, which spin too fast to be held together by their visible matter alone, in the bending of light around massive galaxy clusters, a phenomenon called gravitational lensing, and in the large-scale structure of the universe, where galaxies cluster together in cosmic webs dictated by underlying dark matter scaffolds. Scientists around the globe are building incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a glimpse of a dark matter particle interacting, however rarely, with ordinary matter. These experiments are searching for theoretical particles like weakly interacting massive particles, or WIMPs, which are hypothesized to be the constituents of dark matter. Imagine a particle so elusive it can pass through entire planets without leaving a trace, yet we are trying to detect the 1 in a trillion chance that it might bump into an atom in our detector. It's like trying to catch a ghost with a butterfly net, but a very, very sophisticated butterfly net. Other approaches involve particle accelerators, like the Large Hadron Collider, where scientists smash particles together at incredible energies, hoping to create dark matter particles in controlled conditions. And then there's the cosmic scale, where telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope continue to map the distribution of dark matter through its gravitational lensing effects, giving us a clearer picture of its cosmic architecture. Each new observation, each faint glimmer of an interaction, brings us a step closer to understanding this invisible scaffolding that holds our universe together. But if dark matter is elusive, dark energy is truly mind-bending. It's not just invisible, it seems to be an intrinsic property of space itself, causing it to expand at an ever-increasing rate. Its discovery, remember, came from observing distant Type Ia supernovae, cosmic lighthouses whose predictable brightness allowed astronomers to measure their distances and, crucially, how fast the universe was expanding at different points in cosmic history. What they found was utterly shocking. The expansion wasn't slowing down due to gravity. As expected, it was speeding up. This accelerated expansion leads us to a profound and somewhat melancholic conclusion about the ultimate fate of Milkomda, and indeed, our entire observable universe. While Milkomda will be a magnificent gravitationally bound supergalaxy, a beacon of light in its local cluster, dark energy will ensure its eventual isolation. Over unimaginable timescales, the accelerating expansion will push all other galaxy clusters beyond our cosmic horizon. Imagine standing on an island, watching all other land masses slowly recede until they vanish below the curvature of the Earth, never to be seen again. That's what will happen to Milkomeda, but on a cosmic scale. Other galaxies, even those relatively nearby today, will eventually recede so fast that their light will never reach us. They will effectively disappear from our observable universe, leaving Milkomeda as a solitary island universe. Our descendants, billions upon billions of years from now, if humanity still exists, will look up at a night sky that is virtually empty, devoid of the countless galaxies we can see today. They will have no way of knowing that once, long ago, the universe was teeming with billions of other galaxies, all interconnected and visible. Their cosmological understanding, based only on what they can observe, would be fundamentally different and far more limited than ours. This scenario is affectionately, or perhaps chillingly, known as the Big Freeze, or heat death, of the universe. It's a future where eventually all stars burn out, all black holes evaporate through Hawking radiation, and the universe becomes an incredibly vast, cold and dark expanse, populated only by a dilute sea of fundamental particles, slowly drifting apart into eternal solitude. It's a future that isn't dictated by a dramatic big crunch or a violent big rip, but by a slow, inexorable fade into cosmic oblivion, driven by the relentless push of dark energy. It's a sobering thought, isn't it? That the universe, in its grand finale, might end not with a bang, but with an infinitely drawn-out sigh. Yet even in contemplating such a distant and desolate future, there's immense one will wonder we, in our fleeting moment in cosmic history, are privileged. We exist at a time when the universe is vibrant, dynamic, and full of other galaxies to observe, to study, to marvel at. We are living in a unique epoch where we can witness the cosmic ballet of Andromeda and the Milky Way, and we have the scientific tools to infer the existence of dark matter and dark energy, even if their true nature still eludes us. This journey with Andromeda, from its current state to its future as Milkomeda, has been more than just a tour of a neighbouring galaxy. It's been a profound exploration into the very heart of cosmic mystery. It reminds us that our understanding of the universe is always evolving, always pushing the boundaries of what we thought possible. Every new discovery opens up 10 new questions, and that, my friends, is the true joy and power of science. The universe is vast, ancient, and filled with more wonders than we can ever fully comprehend. It challenges our perceptions, humbles our assumptions, and yet it constantly invites us to look closer, to ask questions, to seek answers. Andromeda, our colossal neighbour, is not just a collection of stars. It's a cosmic mirror reflecting the grandest questions of existence, a living laboratory showcasing the visible and invisible forces that shape everything we know. So the next time you look up at the night sky, and if you're lucky enough to spot that faint, fuzzy patch of light that is the Andromeda Galaxy, remember the incredible story it tells. Remember its immense size, its trillion stars, its inevitable collision course with our home. Remember the brilliant minds who measured its distance and proved its extragalactic nature. And remember the silent, unseen forces of dark matter and dark energy, orchestrating the cosmic dance and charting the universe's ultimate destiny. The journey of discovery never truly ends. It's an ongoing conversation between humanity and the cosmos, a whispered dialogue across unimaginable distances and timescales. And as long as we keep looking up, keep asking how big and why, the universe will continue to reveal its astonishing secrets, one galaxy, one star, one invisible force at a time. The adventure, my friends, has only just begun. We've journeyed through the vastness of Andromeda, marvelled at its scale, observed its stately dance towards our own galaxy, and confronted the profound enigmas of dark matter and dark energy. We understand what they do, how dark matter sculpts galaxies and how dark energy accelerates the universe's expansion. But the fundamental question remains, what are they? This, my friends, is not a frustrating dead end, but arguably the most exhilarating frontier in modern science. It's where our current understanding meets the edge of the unknown, beckoning us forward with the promise of revolutionary insights. Think of it. Two invisible forces, together comprising over 95% of the universe's mass energy, yet utterly mysterious to us. It's like discovering that the vast majority of an iceberg is hidden beneath the surface, and we've only ever seen the tip. The pursuit of these answers isn't just a scientific endeavour, it's a philosophical one, challenging our very perception of reality. How do we, with our instruments and our intellect, hope to grasp something so elusive, so pervasive, yet so stubbornly invisible? The hunt for dark matter is a multi-pronged assault on the cosmic unknown. One primary approach is direct detection. Imagine trying to catch a ghost. That's essentially what scientists are attempting in deep underground laboratories around the world. Why underground? Because cosmic rays and other forms of radiation constantly bombard Earth's surface, creating a noise that would drown out any subtle signals from dark matter. By burying sophisticated detectors kilometers beneath the Earth, they shield them from this interference, hoping to create an environment quiet enough to hear the universe's whispers. These detectors are often giant vats of supercooled liquids, like liquid xenon or argon, designed to be incredibly sensitive. The idea is that if dark matter particles, often hypothesized as weakly interacting massive particles, or WIMPs, are passing through Earth, occasionally one might just bump into an atomic nucleus within the detector. This collision would be incredibly rare, perhaps causing a tiny flash of light or a minuscule vibration, a mere tremor in the cosmic silence. It's like waiting for a single, specific drop of rain in a vast ocean to create a ripple. We haven't definitively caught a WIMP yet, but every non-detection helps narrow down the possibilities, pushing the boundaries of what dark matter could be. Then there's indirect detection. If dark matter particles are their own antiparticles, or if they can interact with each other in other ways, they might annihilate or decay, producing standard model particles like gamma rays, neutrinos, or antimatter that we can detect. Telescopes like the Fermi Gamma Ray Space Telescope scan the cosmos for these telltale signatures. particularly from regions where dark matter is expected to be densest, the centres of galaxies, dwarf galaxies, or galaxy clusters. If we see an excess of high-energy gamma rays coming from the core of Andromeda that can't be explained by ordinary astrophysical processes, well, that would be a very exciting day. And let's not forget our powerful particle accelerators like the Large Hadron Collider, LHC, at CERN. Could we create dark matter particles in the lab? By smashing protons together at nearly the speed of light, we recreate conditions akin to the very early universe, where exotic particles might have been forged. If dark matter particles are created in these collisions, they wouldn't interact with the detectors, but their presence would be inferred by a missing energy signature, a telltale imbalance in the energy conservation equations. It's like throwing two billiard balls at each other, and one disappears mid-air, leaving a gap in the energy tally. Beyond these direct and indirect searches, we continue to rely on the gravitational calling card of dark matter. Gravitational lensing, which we touched on earlier, is a powerful tool here. Remember how massive objects warp space-time, bending the path of light. Dark matter halos, while invisible, are incredibly massive and they do bend light. By observing how light from distant galaxies is distorted as it passes through galaxy clusters, or even the halos of individual galaxies like Andromeda, we can create detailed maps of where the invisible dark matter resides. These maps are not only stunning visualizations of the unseen universe, but also crucial data points for refining our models of dark matter's distribution and properties. Now, what about dark energy? The force driving the accelerating expansion of the universe. Unlike dark matter, which seems to cluster with galaxies, dark energy appears to be smoothly distributed throughout space, a property of space itself. Its nature is even more enigmatic, as it doesn't seem to interact with anything but gravity. Our understanding of dark energy began with observations of various Type Ia supernovae, those standard candles that allowed us to measure cosmic distances. By observing these distant explosions, astronomers discovered that the universe's expansion wasn't slowing down, as gravity would dictate, but speeding up. To further unravel dark energy's secrets, we need to map the universe's expansion history with exquisite precision. This means finding even more supernova, at even greater distances, stretching back further in cosmic time. Future space telescopes, like the Nancy Grace Roman Space Telescope and the Euclid mission, are specifically designed to do this, surveying billions of galaxies and millions of supernovae, to create a cosmic timeline of expansion. But supernovae aren't our only cosmic rulers. We also employ baryon acoustic oscillations, BAO. Imagine the early universe as a hot, dense plasma, a cosmic soup of particles and light. Sound waves rippled through this soup, much like ripples in a pond. These sound waves pushed matter outwards, creating slight overdensities before the universe cooled and these waves froze in place. This left an imprint, a preferred scale, in the distribution of galaxies we see today. It's like a cosmic ruler, a fixed distance, about 490 million light-years today, that we can use to measure how much the universe has expanded since those ripples formed. By mapping the positions of millions of galaxies, we can detect this subtle pattern and use it to gauge the expansion rate at different epochs, providing another powerful constraint on dark energy. And of course, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, continues to be an invaluable source of information. Tiny fluctuations in the CMB temperature and polarization reveal details about the universe's composition, geometry, and expansion rate in its infancy. By combining CMB data with observations of supernovae and BAO, we build a comprehensive picture of our universe's evolution, allowing us to test different models for dark energy. Is it a constant energy density inherent to space itself, Einstein's cosmological constant? Or is it a dynamic evolving field, something we call quintessence, that changes over time? The answer has profound implications for the universe's ultimate fate. The stakes, you see, couldn't be higher. Understanding dark matter will rewrite our textbooks on particle physics, potentially revealing new fundamental forces and particles beyond our current standard model. It will revolutionize our understanding of how galaxies form and evolve, explaining the very structure of the cosmos. Understanding dark energy will determine the ultimate destiny of the universe. Will it expand forever, growing colder and emptier until even atoms are ripped apart in a big rip? Or will dark energy somehow dissipate, allowing gravity to eventually pull everything back together in a big crunch? Or will it lead to the big freeze we discussed, leaving isolated islands like Milky to fade into eternal night? Andromeda, our magnificent neighbour, plays a quiet but crucial role in this grand quest. Its rotation curves, its interaction with its satellite galaxies, its very structure all provide invaluable data points for refining our models of dark matter's distribution and behaviour. By studying the precise dynamics of the Andromeda-Milky Way collision, even from afar, we gain insights into how dark matter halos interact, merge, and influence the bryonic matter within them. It's a cosmic laboratory right on our doorstep, offering a window into the gravitational dance of the invisible. So while the answers to what are dark matter and dark energy remain elusive, the journey of discovery is an odyssey of unparalleled intellectual excitement. We are living in an extraordinary time, witnessing humanity's persistent collective effort to decipher the deepest secrets of the cosmos. Every experiment, every observation, every theoretical model brings us a step closer, slowly peeling back the layers of the universe's profound mysteries. The universe, in its vastness and complexity, continues to humble us, to challenge us, and to inspire us to ask the biggest questions of all. And in that asking, in that relentless pursuit of knowledge, we find our own profound place within the grand unfolding story of existence.